Hi, folks. We are going to talk this time about the periodic table, and we're first going to talk about its invention or conception. The periodic table, many people contributed to its creation, but the gentleman that's given most of the credit is the Russian chemist Dmitry Mendeleev. Mendeleev was looking at all of the elements that were known and discovered by the mid 1800s, and he was trying to make sense out of them. And the story goes like this, that he took all of the known elements at the time and he made, think of them like playing cards. He made individual cards for each element. He put the symbols and the mass of each element on the front, and on the back he wrote what he knew about their properties, what they acted like, what they reacted with, and then he put them in order from the lightest, hydrogen, to the heaviest known elements that existed. The story goes that he would sit around and play a game similar to old-fashioned solitaire, like you'd play with cards, not just on the computer. And he was looking for patterns. Was there any rhyme or reason to what was going on with all of these crazy elements? Well, when Mendeleev was playing with these cards, here's what he did. First off, he took hydrogen. Hydrogen is only one proton, one electron. It's a very unique element. I have a tendency to call it Mr. Special because it is so unique. And he kind of set that aside. But then he took the other known elements, and the noble gases over here were not known at that point in time. So then he started with lithium. Lithium was a soft, shiny metal. You could cut that with a knife. Magnesium, a little bit harder, less reactive than lithium. Boron, carbon, nitrogen, oxygen. By the time you got over to fluorine, it was a very highly volatile reactive gas. The next element he knew about was sodium. Well, he put sodium under lithium. These two were very soft, shiny metals, very explosively reactive with water. And then under beryllium, you had magnesium. Sorry, I have these slightly out of order. Magnesium was, again, a little bit harder, less reactive than its neighbor, sodium. And by the time he got over here, aluminum, silicon, phosphorus, sulfur, chlorine looked and acted a lot like fluorine. These were corrosive, very noxious smelling, never found free in nature, greenish yellow gases. And he found by doing this that periodically certain physical and chemical properties repeated. And he put them in columns or groups that reflected their resemblance to each other. And that's where the name periodic table comes from, because periodically certain physical and chemical properties do repeat. And that's why it has this unusual name. But as we study the periodic table, what you're going to find is location is very important, because if you know the location of an element on the periodic table, you know an awful lot about how it behaves. So as you look at your periodic table, one of the first things that you notice is its states of matter: solid, liquid, gas, or synthetic. On the periodic table I have pictured here, the solids happen to be the black boxes. And there's usually a key or legend on your periodic table telling you what color is what. So most of the elements are solid at room temperature, which is about 68 degrees Fahrenheit or about 20 degrees Celsius. Positive 20 degrees Celsius. And so most elements are going to be solid. A few are liquids. Mercury happens to be a liquid metal at room temperature. Bromine happens to be a liquid nonmetal at room temperature. A few more are gases. All the gases are cuddled up in this corner except for our friend Mr. Special, hydrogen, up in that corner. And then there's this weird collection that are synthetic. Synthetic on this periodic table happen to be outlined in black and are white inside. And what do I mean by synthetic? Well, chemists wanted to discover how atoms are put together. So how do you do that? Well, sometimes you make them yourself. And there's a bunch of really cool stories. Americum, Californium, Berkelium. These were made by a lab out in Berkeley, California, as they were doing a lot of experiments in the mid part of the 1900s trying to understand the atom. And they got the privilege of naming the elements after themselves, well, not themselves, but after their country, their state, and their organization. One of the things that Mendeleev did was he was able to predict the existence of yet unknown elements. So when he created his periodic table, he predicted that elements like gallium, which had not been discovered in the mid-1800s, he predicted where it would fit in the periodic table, he predicted its approximate mass, and he predicted its chemical and physical properties. And he did this with a couple different elements. Long before those elements were found, Mendeleev was able to predict they would exist, and it was because he could use this tool, the periodic table, to predict the existence of yet unknown elements that the periodic table got a lot of acceptance in the scientific community. So this is a big and important piece of scientific equipment. Another real important thing you're going to notice on the periodic table is this. Now, I tend to call it the Stair Steppy line. It probably has a fancy name. I've never found it, but this Stair Steppy line is on all periodic tables. So if we go back here, it is a darker line written right here. And it's very subtle. Sometimes it's easy to not see it right off the bat, but it is an important line because what it does is it separates everything that is classified as a metal from everything that is classified as a nonmetal on the periodic table. And why is that important? That is important because it tells us an awful lot about the properties of the things on the left and the things on the right of the periodic table. So everything on that whole left side of the periodic table are metals. In general, they have a lot of properties in common. At room temperature, they are solids. Most of them have that metallic luster, and you know what a metal looks like faucets and coins and jewelry, that kind of a metallic luster. Most are silver in color. Of course, there are going to be exceptions. Gold is an exception. Copper is an exception. And they are going to reside on that left side of the periodic table. Now, metals in general tend to be malleable. That's a word you need to know. Great quiz question is, what does the word malleable mean? Malleable means that something can be pounded into shape. That's why we can make jewelry out of metal. That's why we can make cooking pots out of metal, because you can bend it into lots of different shapes. They bend and they do not break when we beat on them. Ductile means that you can stretch things into wire. It has to do with the bonding involved, and we will get into that later. But these compounds, how the atoms are stuck together, allows them to be shaped and stretched. And metals tend to be very good conductors of heat and electricity. That's why we use them for electrical wiring, and we use them for cooking pots, because metals are good heat and electrical conductors. Now, the nonmetals reside in that upper right-hand corner of the periodic table above that Stair-Steppy line. These are things like oxygen, phosphorus, sulfur, nitrogen, chlorine, iodine. A lot more variety of color, and they don't have, in their pure state, they don't have that metallic shine. Sulfur certainly is not metallic and shiny. Phosphorus tends to be quite dull. Iodine, right now, it's off-gassing this pretty purple vapor, but in its pure form, it has a little bit of a luster, but it certainly doesn't shine like a new copper penny. Non-metallics tend to be brittle when they are solids, like a diamond. This happens to be a piece of obsidian, not pure, but it's a non-metallic thing. Nonmetals also tend to be poor conductors of electricity and heat, so we use them as electrical and heat insulators. The pink foam that you use to keep your house warm. Hot pads, the insulation we wrap around wires are made out of rubber and plastic. Those things are all made out of non-metallic things from that upper right-hand corner. Even air gaps in glass for insulated windows. What's in there? Plain old ordinary air, which is oxygen and nitrogen. Those things are good at keeping heat from moving, and those are non-metallic things from that upper right quadrant of the periodic table. Now, things that touch that stair-steppy line, well, those are unique and interesting. They are not non-metallic and they are not metallic, so they're somewhere in between, and they are called metalloids. They are sort of metally and sort of non-metally. And everything that has a side that touches the stair-steppy line is a metalloid, except aluminum. It is the big exception. So the metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. These metalloids have a unique set of properties because they have some metal and some non-metal properties. What are they useful for? Well, ladies and gentlemen, their big use is in the computer industry. You have probably heard of Silicon Valley in California. Silicon Valley came about 50 some years ago with the invention of transistors and computer chips, and that is the home of a lot of the computer industry in the United States. And that is because silicon is a big thing that gets used in those chips because it is somewhat metal, somewhat a non-metal. It sort of conducts electricity and sort of doesn't conduct electricity. And all of the things on that stair-steppy line, silicon and germanium specifically, make the best semiconductors. So they're not truly conductors, they are semiconductors. I was just reading something the other day saying that they are actually using arsenic, which is a terrible poison. It's icky stuff, but arsenic can be used to some extent in semiconductor construction. Weird other things, gallium is a funky little metal. Its melting point is it is a solid at room temperature, but the heat of your hand at 98.6 degrees Fahrenheit is warm enough to make it melt in your hand, which is pretty wild and cool. One last thing before we go, talking about the properties of the metals over here, the non-metals up there, and then those metalloids on that stair-steppy line. There are so many more metals. If you look at this, there's 2/3 metals and less than 1/3 non-metals over there. So if there's so many metals, why isn't the entire world that you and I live in silver and shiny? Well, a couple answers to that question. One, the Earth's crust that you and I inhabit is mostly made of oxygen, silicon, and aluminum. Those are the three most abundant elements on the surface of the Earth. Oxygen, silicon, and aluminum all reside up in this corner. That's what's on the surface of the Earth. Most of the metals are heavy, they're dense, and they are down inside of the core of the Earth. They're heavy, and when the Earth was molten, it parfaited out. The heavy stuff is down in the center of the Earth when the Earth was young and hot. The other reason that most of the world that you and I see is not silver and shiny is that most of the things that you and I observe are bonded. We don't see the elements in pure form, almost never. We see the elements bonded with other things, and that's why for a great deal of this course, we are going to talk about bonding. How do elements bond with other elements to make everything from sugar to water to the oxygen that we breathe? All right, we will see you later. Bye-bye.